Recording has started.
Alright, so we are going to look at a few animations to better understand what's going on in this MOS structure when we change the gate voltage. So here we show the charge density and electric field and the electric potential of the MOS structure like this. And this animation is done by the real simulation. It's actually more accurate than what we derived using the simple equations in the past few slides. This one is through the physical numerical simulations. This is for the NA damping density, p-type, 10 to the power 18 per centimeters cube. So if you have this damping density NA, you can calculate what is the phi b, and or let's say what is 2 phi b. Then with this NA, if you use equations for the phi b, you will find the 2 phi b is like 0.93 volts. Okay, so let's get started from the zero voltage. At zero voltage, nothing will happen. But let's increase the voltage, let's say, to be 0.2 volts. And in this case, the phi s, the surface potential, actually is only 10% of the 2 phi b. And you look at the charge density here. So we see some negative charge here. This is actually the depletion charge. So you have the Na minus here. And then you apply a very small voltage. This is only 0.2 volts here from the gate. But this 0.2 volt actually dropped across the oxide first. And then the phi s on the depletion region. So let's move on, and you will see the change. So let's increase the gate voltage. So through this process, you see that the depletion width will increase. This WD will increase. This is because we push away the hose further. But this is only 0.6 of the 2 phi b. We need to reach 2 phi b to get the strong inversion. So let's keep doing that. This is 0.7, 0.8, 0.9. Okay, so now the gate voltage is 1.25 volts, and the phi s is 90% of the 2 phi b. So it's kind of approaching the threshold condition. So you see that the surface of the silicon, you see a little bit, let's say, more negative charge here. That means we are going to about to induce the electrons. And then let's move to the threshold condition. So now the gate voltage is 1.38. So this is exactly the threshold voltage because now the phi s is 2 phi b, exactly 2 phi b. So what is the phi s? Phi s is here. This is the phi s. And this is your gate voltage. And part of the gate voltage dropped on the oxide, VOX. And part of that is on the phi s. So now you see the surface has a peak of the negative charge. So this is the inverted electrons. So this is a strong inversion. And then let's further increase the gate voltage above the threshold. You see what will happen. So this inversion will become stronger and stronger. That means you have more and more negative electrons here. Actually, we have to draw this because here we didn't change the scale, so this is out of the scale. But if you want to draw it in the full scale, then it's like this. So we have more and more negative electrons here. And if you compare, let's say, the depletion width, actually it will not change too much. This is threshold. After threshold, if you look at this, the depletion width, it will almost no change. You see here, we already increased the gate voltage from the threshold voltage 1.35 to this 2.2 volts, but still the WD does not change too much. So this is one conclusion. After the threshold voltage, then the WD depletion width almost no change. And also another parameter you want to pay attention to is this phi s. This phi s. After the threshold voltage, this phi s is also almost constant. You look at this animation, phi s here does not change too much. Then what is changing? Actually, you keep increasing the gate voltage. This phi s is almost fixed. Then what is increased in this VOX? In other words, after the threshold voltage, the more gate voltage you apply, the more voltage drop across the oxide instead of the silicon surface. So any questions here? All right, then let's look at the band diagram of the MOS structure. And this is the flat band at the 0 voltage, Vg equals to 0. So this is a band. We have the flat Fermi level from the metal to the silicon, and this is p-type. So EF is close to the EV. So this is the initial state, and then we increase the gate voltage to positive voltage. So we increase that. So you see that as we increase the gate voltage, then we push down the band of the Fermi level of the metal, and then to the bulk of the substrate, it will be flat. But the surface is bent down. And actually, when we reach the phi s, 60% of the 2 phi b, or let's say even 50% of the 2 phi b. So you see here at the surface, the Fermi level, the black curve, actually reach the red curve, which is the the red curve is the EF, and the black curve is the EI, the intrinsic Fermi level, which is the middle of the band gap. So here, if the phi s is half of the 2 phi b, or in other words, phi s is the same as the phi b. So basically, at the surface, the EI and EF will overlap. So this is actually a switching point between the p-type to n-type. But we didn't use this one as a definition of the threshold, because this is only a weak inversion. So for example, here we keep increasing the voltage, the phi s becomes 60% of the 2 phi b. So now actually the Fermi level, the red one, is above the EI, the black one. So that means this is actually n-type already. But it's not strong enough. So we call this as a weak inversion. So if you compare the electron density here to the surface with the hole density to the bulk, still the electron density to the surface is less than the hole density of the bulk. So this is weak inversion. And we need to reach the strong inversion where, let's say, if you keep moving, now we are at the threshold condition. So the phi s is 2 phi b, So at this point, we will see the electron density at the surface is the same as the hole density of the bulk. Why is that? So in this case, if you look at the surface, so this red line is the EF and the black line is the EI. So to the surface, the EF is above EI by phi b, right? And to the bulk, the EI, EF is below EI by phi b. Or if you look at the distance, EF to the EC and the EF to the EV here, they are the same in this case. Or in other words, here the EC minus EF is the same as this EF minus EV here. So remember, this is the surface and this is the bulk. So EC minus EF here at the surface will determine the the electron density, and the EF minus EV to the bulk will determine the hole density. And if this distance is the same, then you know the hole density and the electron density will be the same. So this is a threshold condition, this strong inversion. And if you further increase the gate voltage above the threshold, then here this phi s will not change anymore. So what it will be changed is this slope in the oxide as you further push down the band. Then this one will not change too much, and then additional voltage will drop on the oxide to further bend down the oxide, but the semiconductor will not further bend down. So this is the band diagram as a function of the gate voltage. Any questions? All right, so let's summarize what are the important messages, take-home messages for today. I think the first one is understand how to create the inversion. So basically, the surface of the silicon needs to be pushed down by 2 phi b in terms of the band edge. So we define this as a phi s, and phi s equals to 2 phi b. And then understand the band diagram in different conditions, the accumulation, flat band, depletion, inversion. And then understand the charge balance across this capacitor. The positive charge equals to the negative charge. And then this derivation, we don't require that, but the eventual conclusion is important here. You should be able to calculate what is the threshold voltage if we give you the doping density and the thickness of the capacitor, the TOX. Then you can calculate the COX, you can calculate phi b, and then the others are physical constants like the epsilon and the Q. And then you can play those animations by yourself after class to further understand what's going on in the MOS structure in terms of the charge density and also the electrical potential, and then the band bending here. So one conclusion is that when you reach the threshold voltage, then the depletion width will no longer increase, is almost constant after the threshold, and also the phi s here is almost a constant, no more increase after the threshold. All right, any other questions? I got one question. Why is EF not bounded despite an external electric field? Okay, that's a good question. So here, this MOS structure is a capacitor structure. When we apply the DC voltage like this, there's no current flow. No current flow means it's in the equilibrium state. In the equilibrium state, in the, let's say, in the silicon, there's no current. So in the silicon, the Fermi level should be flat. But the Fermi level of the metal and the Fermi level of the silicon will have a difference. That difference is caused by the gate voltage you applied here. But in the silicon, since there's no DC current flowing in this case, then you should have a single Fermi level. This is like the equilibrium state, at least in the silicon. All right. Any other questions? Then if not, then we can stop here today, and I think you should be able to solve all the questions for homework 2. All right, and that's it. Thank you. Bye-bye.